The M1 Abrams is powered by a 1,500 shaft horsepower, 1,100 kilowatts, Honeywell AGT 1500 gas turbine engine, giving it a governed top speed of 45 miles per hour, 72 kilometers per hour, on paved roads, and 30 miles per hour, 48 kilometers per hour. Cross-country. Tank power output and torque in context. Vehicle power output. Power forward / weight torque. Mid-sized car. Toyota Camry 2.4 L 118 kilowatt, 158 HP, 79 kilowatt forward / T, 106 HP forward / T, 218 Nm, 161 lb-f foot. Sports car. Lamborghini Murcielago 6.5 L 471 kilowatt, 632 HP, 286 kilowatt forward / T, 383 HP forward / T, 660 Nm, 490 lb-f foot. Racing car. Formula 1 car 3.0 L 710 kilowatt, 950 HP. 1065 kilowatt forward / T, 1428 HP forward / T, 350 Nm, 260 lb-f foot. Main Battleton Leopard 2, M1 Abrams 1,100 kilowatt, 1500 HP, 18.0 to 18.3 kilowatt forward / T, 24.2 to 24.5 HP forward / T, 4,700 Nm, 3,500 lb-f foot. Locomotive SNCF Class T2000 1,925 kilowatt, 2,581 HP, 8.6 kilowatt forward / T, 11.5 HP forward / T. Operational mobility. Strategic mobility. A Pakistani Zara MBT crosses an armored vehicle launched bridge during night exercises in 2016. Strategic mobility is the ability of the tanks of an armed force to arrive in a timely, cost-effective, and synchronized fashion. For good strategic mobility, transportability by air is important, which means that weight and volume must be kept within the designated transport aircraft capabilities. Nations often stockpile enough tanks to respond to any threat without having to make more tanks, as many sophisticated designs can only be produced at a relatively low rate. The US, for instance, keeps 6,000 MBTs in storage. 80. In the absence of combat engineers, most tanks are limited to fording small rivers. The typical fording depth for MBTs is approximately 1 m, 3.3 feet, being limited by the height of the engineer intake and driver's position. Modern tanks such as the Russian T-90 and the German Leopard 1 and Leopard 2 tanks can ford to a depth of 3 to 4 m, 9.8 to 13.1 feet, when properly prepared and equipped with a snorkel to supply air for the crew and engine. Tank crews usually have a negative reaction towards deep fording, but it adds considerable scope for surprise and tactical flexibility in water crossing operations, by opening new and unexpected avenues of attack. Amphibious tanks are specially designed or adapted for water operations, such as by including snorkels and skirts, but they are rare in modern armies, being replaced by purpose-built amphibious assault vehicles or armored personnel carriers in amphibious assaults. Advances such as the EFA mobile bridge and armored vehicle-launched scissors bridges have also reduced the impediment to tank advance that rivers posed in World War II. 81. Crew. The tank commander's position in an AMX Leclerc positions of crew members in a Russian T-72B3 tank. The driver, 3, is seated in the vehicle's front. Commander, 1, and gunner, 2, are positioned in the turret, directly above the carousel, 4, which contains the ammunition for the autoloading mechanism. Most modern tanks most often have 4 crew members, or 3 if an autoloader is installed. These are the commander. The commander is responsible for commanding the tank, with all-round vision devices rather than the limited ones of the driver and gunner. He guides the gunner roughly onto target and guides the driver around turns and obstacles. The gunner is responsible for laying the gun, the process of aiming an artillery piece at targets. It may be laying for direct fire, where the gun is aimed similarly to a rifle, or indirect fire, where firing data is calculated and applied to the sights. The term includes automated aiming using, for example, radar-derived target data and computer-controlled guns. Gun laying means moving the axis of the bore of the barrel in two planes, horizontal and vertical. A gun is traversed, rotated in a horizontal plane, to align it with the target, and elevated, moved in the vertical plane, to range it to the target. The loader loads the gun, with a round appropriate to the target, heat, smoke, etc., as ordered by either the commander or the gunner. The loader is usually the lowest ranked member of the crew. In tanks with autoloaders this position is omitted. The driver drives the tank, and also performs routine maintenance on the automotive features. A view in AM-101 Abrams tank of the gunner's station, bottom left, and commander's station, top right. Operating a tank is a team effort. For example, the loader is assisted by the rest of the crew in stowing ammunition. The driver is assisted in maintaining the automotive features. 82. Historically, crews have varied from just 2 members to a dozen. First World War tanks were developed with immature technologies. In addition to the crew needed to man the multiple guns and machine guns, up to 4 crewmen were needed to drive the tank. The driver, acting as the vehicle commander and manning the bricks, drove via orders to his gearsmen. A co-driver operated the gearbox and throttle, and 2 gearsmen, one on each track, by setting one side or the other to idle, allowing the track on the other side to slew the tank to one side. Pre-World War II French tanks were noted for having a 2-man crew, in which the overworked commander had to load and fire the gun in addition to commanding the tank. With World War II the multi-turreted tanks proved impracticable, and as the single turret on a low-hull design became standard, crews became standardized around a crew of 4 or 5. In those tanks with a 5th crew member, usually 3 were located in the turret, as described above, while the 5th was most often seated in the hull next to the driver, and operated the hull machine gun in addition to acting as a co-driver or radio operator. Well-designed crew stations, giving proper considerations to comfort and ergonomics, are an important factor in the combat effectiveness of a tank, as it limits fatigue and speeds up individual actions. Engineering constraints. The Indian Arjun MBT should drop pneumatic suspension at work while moving over a bump track. A noted author on the subject of tank design engineering, Richard Agorkiewicz, outlined the following basic engineering subsystems that are commonly incorporated into tanks' technological development. Smiley 83, Mobility of tanks, through chassis design. Tank engines. Tank transmissions. Suspensions and running gear. Soil vehicle mechanics. Tank guns and ammunition. Ballistics and mechanics of tank guns. Vision and sighting systems. Illuminating and night vision systems. Fire control systems for main and auxiliary weapons. Gun control systems. Guided weapons. Armor protection. Configuration of tanks. To the above can be added unit communication systems and electronic anti-tank countermeasures, ergonomic and survival systems, including flame suppression, and provision for technological upgrading. Few tank designs have survived their entire service lives without some upgrading or modernization, particularly during wartime, including some that have changed almost beyond recognition, such as the latest Israeli Magak versions. The characteristics of a tank are determined by the performance criteria required for the tank. The obstacles that must be traversed affect the vehicle's front and rear profiles. The terrain that is expected to be traversed determines the track ground pressure that may be allowed to be exerted for that particular terrain. 84. Tank design is a compromise between its technological and budgetary constraints and its tactical capability requirements. It is not possible to maximize firepower, protection and mobility simultaneously while incorporating the latest technology and retain affordability for sufficient procurement quantity to enter production. For example, in the case of tactical capability requirements, increasing protection by adding armor will result in an increase in weight and therefore decrease in mobility. Increasing firepower by installing a larger gun will force the designer team to increase armor, the therefore weight of the tank by attaining same internal volume to ensure crew efficiency during combat. In the case of the Abrams M-Beat, which has good firepower, speed and armor, these advantages are counterbalanced by its engine's notably high fuel consumption, which ultimately reduces its range, and in a larger sense its mobility. Since the Second World War, the economics of tank production governed by the complexity of manufacture and cost, and the impact of a given tank design on logistics and field maintenance capabilities, have also been accepted as important in determining how many tanks a nation can afford to field in its force structure. Some tank designs that were fielded in significant numbers, such as Tiger I and M62, proved to be too complex or expensive to manufacture, and made unsustainable demands on the logistics services support of armed forces. The affordability of the design therefore takes precedence over the combat capability requirements. Nowhere was this principle illustrated better than during the Second World War, when two Allied designs, the T-34 and the M4 Sherman, although both simple designs which accepted engineering compromises, were used successfully against more sophisticated designs by Germany that were more complex and expensive to produce, and more demanding on overstretched logistics of the Wehrmacht. Given that a tank crew will spend most of its time occupied with maintenance of the vehicle, engineering simplicity has become the primary constraint on tank design since the Second World War, despite advances in mechanical, electrical and electronics technologies. Since the Second World War, tank development has incorporated experimenting with significant mechanical changes to the tank design while focusing on technological advances in the tank's many subsystems to improve its performance. However, a number of novel designs have appeared throughout this period with mixed success, including the Soviet IT-1 and T-64 in firepower, and the Israeli Merkava and Swedish S-tank in protection, while for decades the US M551 remained the only light tank deployable by parachute. Command, control, and communications. German Army Leopard 2 A6M incorporates networked battlefield technology. Commanding and coordinating tanks in the field has always been subject to particular problems, particularly in the area of communications. But in modern armies these problems have been partially alleviated by networked, integrated systems that enable communications and contribute to enhanced situational awareness. 20th century. World War I and interwar period. Armored bulkheads, engine noise, intervening terrain, dust and smoke, and the need to operate buttoned up, with hatches closed, are severe detriments to communication and lead to a sense of isolation for small tank units, individual vehicles, and tank crew. Radios were not then portable or robust enough to be mounted in a tank, although Morse code transmitters were installed in some Mark IVs at Cambridge's messaging vehicles. 85. Attaching a field telephone to the rear would become a practice only during the next war. During World War I, when this failed or were unavailable, situation reports were sent back to headquarters by some crews releasing carrier pigeons through loopholes or hatches. 86. And communications between vehicles was accomplished using hand signals, handheld semaphore flags which continued in use in the Red Army/Soviet Army through the Second and Cold Wars, or by foot or horse-mounted messengers. 87. World War II. From the beginning, the German military stressed wireless communications, equipping their combat vehicles with radios, and drilled all units to rely on disciplined radio use as a basic element of tactics. These allowed them to respond to developing threats and opportunities during battles, giving the Germans a notable tactical advantage early in the war. Even where Allied tanks initially had better firepower and armor, they generally lacked individual radios. 88. By mid-war, Western Allied tanks adopted full use of radios, although Russian use of radios remained relatively limited. Cold War era. Merkava Mark IV main battle tank is equipped with a digital C4's battle management system. On the modern battlefield, an intercom mounted in the crew helmet provides internal communications and a link to the radio network, and on some tanks an external intercom on the rear of the tank provides communication with cooperating infantry. Radio networks employ radio voice procedure to minimize confusion and chatter. A recent development in AFV equipment and doctrine is integration of information from the fire control system, laser rangefinder, global positioning system and terrain information via hardened military specification electronics and a battlefield network to display information on enemy targets and friendly units on a monitor in the tank. The sensor data can be sourced from nearby tanks, planes, UAVs or, in the future, infantry, such as the U.S. Future Force Warrior project. This improves the tank commander situational awareness and ability to navigate the battlefield and select and engage targets. In addition to easing the reporting burden by automatically logging all orders and actions, orders are sent via the network with text and graphical overlays. This is known as network-centric warfare by the US, Network-Enabled Capability, UK, or Digital Army Battle Management System, Israel. Advanced battle tanks, including the K2 Black Panther, have taken up the first major step forward in adopting a fully radar-integrated fire control system which allows it to detect tanks from a further distance and identify it as a friend or foe, as well as increasing the tank's accuracy as well as its capability to lock on two tanks. 21 ST Century. Circular review system of the company Limpid Armor performing situational awareness and communication is the one of our primary MBT functions in the 21st century. 89. To improve the crew's situational awareness, MBTs use circular review system with a combination of augmented reality and artificial intelligence technologies. 90. Further advancements in tank defense systems have led to the development of active protection systems. These involve either one of two options: soft kill. The soft kill protection systems use integrated onboard radar warning receivers which can detect incoming anti-tank missiles and projectiles. Once detected, soft kill measures will be deployed, which involves deploying smoke screens or smoke grenades which interfere with incoming missiles' infrared tracking system. This will cause the incoming missile to miss tank or to deactivate entirely. Hard kill. The more advanced approach involves the hard kill measures. These involve directly destroying the incoming enemy missile or projectile by deploying the tank's own anti-missile projectile. This is seen as a more reliable approach due to its direct intervention measures rather than interference measures of the soft kill systems. Both these active protection systems can be found on several main battle tanks including the K2 Black Panther, the Merkava and the Leopard 2A7. Combat milestones. Conflict year. Total number of tanks. Notes. Battle of the Somme 191649 tanks first used in battle, 91, 92. Battle of Cambrai 1917-378 first successful use of tanks, 93. Second Battle of Villas Bretano 1918-23. First Tank vs. Tank Battle Spanish Civil War 1936-1939 700 Interwar Tanks in Combat Invasion of Poland 1939 8,000 Origin of Blitzkrieg Term Battle of Hanut, Belgium 1940